Good morning, everybody. We're just waiting for all the attendees to trickle in, and we'll start the webinar in a couple minutes. We're going to go ahead and get started. So good morning, everybody. Welcome to the RCN webinar for SARS-CoV-2 and wastewater. Today we have two speakers. One is Catherine Hoar, who is a postdoc, of course, at NYU, and then Jessica Deaver, who is a student at Clemson. And so the way this works, for those of you who are new, the questions for the speakers you post in the Q&A, not in the chat. The chat is for communicating like other issues that you might be having. And you have the ability to upvote questions. So as you're looking at the Q&A, you can give a thumbs up to questions that you're interested in hearing the answer to. And so there will be moderators who oversee the Q&A, and we'll be going through those questions. The attendees don't have the ability to speak, but we can allow you to speak if there is a question that requires some oral communication back and forth. So with that, we're going to go straight into the presentation by Catherine. So please go ahead, Catherine. Thank you.
Thank you. Good morning. My name is Catherine Hoar. I'm a postdoc in Andrew Silverman's lab at NYU, and I really appreciate the opportunity to talk today and share some of the experiences we've had working with New York City on this project. So the city's SARS-CoV-2 wastewater monitoring program, like so many others, is really a big collaborative effort made possible by a partnership between, on the academic side, New York University and colleges in the City University of New York or CUNY system, Queensborough Community College and Queens College, and then on the municipal side, the New York City Department of Environmental Protection, or DEP. And you'll actually hear in an upcoming seminar in a couple of weeks from Zach, who's a member of the CUNY team. So the city had some pretty clear goals from the onset for how they wanted this program to operate, with the main goal being to be able to quickly assess trends throughout the boroughs by looking at influent from the 14 wastewater treatment plants in the city. And then another really important part for the city was to have this program be completely in-house, meaning that the entire process, every part of the analysis would be completed in existing DEP facilities by DEP personnel, so that it would really become more a part of their overall monitoring program. And in a lot of ways, the structure for this type of system was already in place, which was really, really helpful. For example, the sampling sort of fit in with some of the structure of sampling they had already for microbial analysis that they do. So that was good. And there was also, some equipment, and some of the expertise was there, but definitely for this project, there was a lot of new investment and capacity building that was required. So I would say on the order of weeks, the DEP was able to set up a molecular biology lab in one of their existing labs. And I think what's recognized now as a real benefit of building this kind of in-house program is that the department now has the ability in the future to potentially look at other organisms of concern because they have this system established already. And so for this pandemic to accomplish these goals on what we all know is a really short time frame, we needed a clear, relatively simple and reproducible protocol that could be carried out in their lab by their analysts, and that ideally took advantage of some of the equipment that they already had in their lab. And so this was that protocol. This method was developed by members of the CUNY team. Originally, they developed this method with some other endpoint analysis in mind. And as I mentioned, Zach will be presenting, and I'm sure he'll talk about some of the optimization strategies and development of this method. But just briefly, we're taking 40 mil influent samples and we're pasteurizing, and then we're spiking in bovine coronavirus as a control before centrifugation for solid separation and filtration. And then we concentrate the samples with the PEG and then extract with a QIAGEN QIAAMP viral RNA kit. And then we're using a one-step RT-qPCR assay for the N1 target for SARS-CoV-2. And then we're also looking at bovine coronavirus, our control. And for some of the plants, we've been looking at pepper mild mottle virus. And so we know that there are kind of an overwhelming number of options when it comes to methodology. And we ourselves sort of at each of these steps saw a decision point to make. But this method really worked well for the DEP based on the equipment that they had for them to get started in a short time frame. And the CUNY team was having a lot of luck with it. So they moved forward and were able to start up routine sampling around the end of August. But then as analysis began, questions and sort of logistical issues came up that required some optimization that the team was able to look into. And I'm going to talk about some of those today. I'll just note here what's been really great about, what I think is really great about the program DEP is set up is that a lot of this optimization and testing is actually taking place in the lab where the routine analysis is happening by the analysts who are doing the daily work. So in that way, this optimization sort of inherently included some training as well as consideration of ease of use for analysts and logistics at the site. So in parallel with developing this program for them, we were also working on looking at some of the more scientific fundamental questions about the method. And this approach certainly wasn't without its challenges, but I think something that came out of it was a real ownership and understanding on everyone's part of each of the steps of why we included certain steps and why we were doing things the way we were. And then also input from everyone on how we can improve this method for this specific application at this specific site. So, having everyone a part of the startup and the optimization really made for this kind of fast-paced, sort of on-the-go optimization hybrid training experience, which I think was really useful. So one of the first things we were curious about during optimization was the effect of pasteurization. So we had done some preliminary work with a slightly different PEG concentration method in the summer, and we saw that pasteurization actually decreased our signal of the bovine coronavirus control that we had. So based on that observation, we were actually initially considering eliminating pasteurization altogether. But then we're also hearing sort of other things about the response of N1 or SARS-CoV-2 targets due to pasteurization. So what we wanted was, a quick way to assess what the effect of pasteurization was on our targets and whether that effect was consistent for each target. So we looked at a few different plants for this quick study. And on this chart, we're looking at concentrations of the N1 target in copies per liter. So, higher being better, higher recovery. And we ran the same samples from a plant, both pasteurized and unpasteurized, in duplicate. So the pasteurized are in those darker circles, and the unpasteurized are in the lighter squares. And we see that for N1, for this PEG method, we do see slightly higher N1 signal after we pasteurize. And the asterisks there are just indicating a significant difference between pasteurized and unpasteurized. Now, the magnitude of this difference really isn't big, and it's not big enough to get in the way of understanding general trends, but there is a difference there. A couple of things to note: we also tried looking at this without filtration. So we had a filtration step in our method. We did the exact same thing on samples that weren't filtered and saw the same trend, the same pattern for N1 after pasteurization. And then another thing is that we had done some preliminary work looking at concentration with absorption using HA filters. And we actually saw the opposite trend, meaning that, with the HA filters, we actually saw that pasteurization decreased the N1 signal. So this is something we definitely would need to look into more, but are certainly curious if others have results related to this. And so if we look at our other targets for these same samples, on the left, the bovine coronavirus, very slight, but we are seeing a decrease in signal due to pasteurization. And then for PMMOV, there's really no significant or consistent trend due to pasteurization. So the response of these targets are different than for N1. And this was a really important lesson for us, thinking about using other viruses or other targets during optimization. The difference here, the magnitude of the difference wasn't huge, so it didn't really end up mattering that much, but just being aware that these different targets or potential surrogates could behave differently due to different steps. And I know this is something that has been discussed a lot. So another thing that we looked at was the effect of filtration. The team had started their analysis using these 0.22 micron cellulose acetate filters. And then sometime in the fall, we actually ran into supply chain issues and weren't able to acquire any more of these filter setups. There were some other filter setups available, different sizes and materials. And so, we were sort of forced to consider either using these or not filtering anymore. And what we sort of needed to assess was whether filtration was necessary. Was filtration critical for the success we were seeing with our method? And if we did want to sub in another filter, how would that affect our results? Could we compare different results from using the other filters? So these results are from early October. Actually, I should have mentioned the previous results were from late September, early October. So we're seeing now with higher cases, definitely higher concentrations of N1 in our wastewater samples. But in early October, the team doing routine analysis was able to check samples with and without filtration to get an idea of the effect. So we looked at 3 different filters. The first 0.22 micron filter is this filter that they originally started with and are back to using now. And these 2 other filters are these temporary replacement filters. So a 0.45 micron cellulose nitrate filter and another 0.22 micron filter, PS. So it looks like in general, the order of magnitude of N1 concentrations, viral concentrations in these samples is the same depending on whether you filter or not, but the effect of different filters, particularly with the type of filter, is definitely different. For example, if we look at the 0.45 micron filter, it looks like not filtering actually increases our N1 concentrations in the samples. So based on this, initially we were thinking if 0.2 filters, cellulose acetate filters aren't available, maybe it's better not to filter at all. But then some other factors and insights came into play. It's possible that in this lab, filtering actually reduces variability. So if we look at the error bars on our filtered samples, most of them are actually smaller than the error bars on the unfiltered samples. And in talking to the analysts, for them, it made more sense. It was easier. It felt more consistent to be filtering to avoid taking up any loose pellet after solids removal with centrifugation. So they actually preferred to be using the filters. They felt that it flowed better for them and made it easier for them. Another really important part that we discovered is that when we remove filtration, it actually really slowed down our RNA extraction step. So the lab is using a vacuum manifold for RNA extraction with a Chi-amp kit. And when we didn't filter, the spin columns were just clogging very easily, and it was taking a lot longer for them. So it made sense, you know, despite possible shifts for the lab to keep filtering so that they could keep moving at the speed they were for the routine monitoring they were doing. Another thing to consider that we weren't thinking about at the time, but there are benefits of filtration that maybe would come into play for other downstream processing or analysis. So for example, if we're considering sequencing this RNA later, maybe it's a really good idea to be filtering when we can. So we also looked at some other concentration methods. As I mentioned, we did some preliminary work with HA filters, but that has not been optimized at all. It was just sort of a quick look that we've done so far. And then we also looked at direct extraction of the samples without any concentration. So these are those same treatment plants that we've looked at with the pasteurization. And here we're looking at those samples both with PEG concentration in the darker circles and without any concentration, direct extraction in the open circles. And there are in fact error bars on the PEG concentrated samples. They're just too small to see. But as you can see, the error bars are very large on the direct extractions, and it's really more of an estimate. So if we go over to our CT values from RT-qPCR, we see that a lot of these pretty much all of these direct extractions were below our limit of detection and certainly below our limit of quantification. And we had a lot of non-detects. So, you know, as expected, we had to concentrate these samples to quantify. You know, it's conceivable at some unfortunate point that concentrations might be high enough in the city that concentration wouldn't be necessary and direct extractions could be used. But from our perspective and trying to keep things consistent, it makes more sense for us to be using one method with, you know, relatively consistent recovery to be able to compare over time and to really avoid this territory of being below the limit of quantification. With the acknowledgement and the understanding that there is loss during these concentration methods, and certainly for viruses that had higher concentrations in our samples, so the bovine that we spiked in or pepper mild model virus, we were able to quantify with direct extraction, and certainly that recovery was higher than with PEG. And the last part of the method that I want to touch on has to do with RNA extraction. As I mentioned, Zach is going to talk in a couple of weeks, and he'll explain some of the different RNA extraction optimization that the CUNY team did, looking at different methods of RNA extraction and working with the PEG pellet. What I'm going to talk about, you can think of the sort of part one, is more of a logistical issue that came up related to the kit. So one modification that the CUNY team made to the RNA extraction kit is the addition of the lysis buffer directly to the PEG pellet and increasing that lysis buffer volume about 3 times the recommended volume. And this was really to ensure that the full pellet was resuspended and we were recovering as much as we could, because that was a challenge. And this was working really well with triple the lysis buffer volume. But using that much more of the lysis buffer does have logistical issues related to, you know, you're using more of the reagent, so supply chain and cost, and then it does take a little bit more time for the RNA extraction when you add that much more volume. If you're thinking about expanding how many samples the team wants to run. And then also the lab is thinking about exploring automating some of these steps, and having changed or larger volumes can make that trickier. So what we wanted to look at was, can we have similar success by looking at a lower lysis buffer volume? And so during routine analysis in December, you can see the N1 gene copies are a little bit higher now in these samples. We looked at a slightly lower volume of lysis buffer added. And we see, which was really promising, that there really is no significant difference. So we can successfully recover the same amount of virus if we use a little less lysis buffer. And for us, that was really good to know, because we can reduce the amount that we're using potentially, and that could be really helpful. So all of this optimization and analysis was happening during routine sampling that the lab was doing. And again, these were influence samples. They're 24-hour composite samples that are collected twice a week. So it was a lot going on at one time. And I just want to show a summary of some of the results from the startup in late August to now. And I know it's a little hard to see them all together like this, and I'm realizing maybe my face is blocking some of them, but on the primary left y-axis, we're looking at N1 gene copies per day, gene copies concentrations normalized by flow rate and population in the sewer shed. And those are the blue circles with the low S curve in black. And then on the secondary, the right y-axis, we're looking at a 7-day average of cases per 100,000 people in that red line. And that's from publicly available data from the city. So in general, we're seeing a pretty good fit between these trends. We're working on now trying to better quantify the correlations between the health data and the wastewater data, and looking at potential lag on those correlations. And so, a lot more to be done on the data analysis side, but some big takeaways from our methodology work is that, different steps like pasteurization really might have a different effect depending on the target, as well as the other parts of the process. So the concentration method, for example. And then there are benefits to certain steps that may really depend on what your downstream analysis will be. But what's really key, I think, is that the city is equipped now to assess any future modifications or optimization on their own, because the city had the goal of setting up this system in-house. And so obviously this work took a big network of people, especially in New York City Department of Environmental Protection and the Bureau of Wastewater Treatment, and in our academic partners as well. Thank you.
Thank you, Catherine. That was a really great presentation. A lot of really good stuff in there. It's exciting to see all these programs developing so much. Just a reminder, if anyone has questions, please put them in the Q&A. I'll start with the ones that are there, and you can upvote ones as they're added. So we do have one question here now. Wondering how the results from your monitoring are shared and used by public health departments, and whether or not the data is available to the public as well.
Sure, yeah. So right now it's not available to the public, but the DEP is sharing on a weekly basis this information with the New York City Department of Health. Yeah, so that's how it's happening right now.
Okay. Yeah, do you know if they're actively using that data in the health department, or are they starting to just receive it at this point? I know that can be a tricky thing to work out. So
there's a lot of interest. I mean, I think like most public health agencies, they're really overwhelmed at the moment, and they're still thinking through like how to use this data and how to work with some of the variability in the data, because there definitely is a lot of it. So at the moment, there's no actionable steps that are being taken based on the data, but they're definitely interested and they're getting it.
Sure. Okay, and I have a couple other questions here. One just came in the Q&A. For your LOD and LOQ, how do you assess those? So what are they based on for your assay?
Yeah, sure. So for the LOD, I think that's what 95% of a standard that we're running shows up in qPCR, and then the LOQ, it's I'm forgetting the exact equation right now, but it's based on variation and a reduced variation, I think like below 35% of a given standard.
Okay. And awesome, these questions are coming in right as you finish your answer. If you had advice to labs who are just starting this up, going through that full, logistics with monitoring and training at the same time process, what would be your one piece of advice for getting that up and running?
Ooh, that was a good question. I think for us, like having everyone involved was just really key. So I think it's tempting, especially in the academic side, to sort of, I want to think about how to make this perfect before presenting it to anyone. But it was really useful to have the analysts there and working with us. And there were so many insights that came up and things that I wouldn't have thought of, thinking of this on a bigger scale, sort of lab that was trying to output a lot of data. So including everyone, I think was really a big, important part for us.
Yeah, that seems like a really important piece. And then one question about your concentration method. So I think a lot of people are interested in, improving speed of the process and repeatability. Some people are using these concentrating pipettes. So curious if you are, when you went through that process, how is the speed of the process? Maybe you can let us know how quickly you're able to turn around sample processing, and if you're still working on making that faster, or has the lab kind of gotten happy with where they're at?
Sure, yeah. So the big bottleneck in the beginning was the centrifuge. So the number of spaces is obviously limited, and that PEG is it's a 2-hour spin for us. And PEG itself is a pretty long process. So overall, I think the data comes out after 2 days of analysis, because it's sitting overnight in 4 degree. So it's definitely one of the longer of the options. But the DEP has acquired a larger new centrifuge, so that's definitely exciting, and it lets them do a lot more.
Yeah, and I know you mentioned at the beginning that working with them, some of it is based on the equipment that they have and maybe the expertise that they're like comfortable with, and that sort of thing is a big part. Okay, I think we have maybe time for one more question. I have a quick one in my messages from Rolf, just asking how long was your pasteurization step when you did that on samples? Sorry, was that 90 minutes? Keep talking over you, sorry. And okay, I think we might be just about done on time if there's no other question. Oh, there are a few other questions. I think we don't probably have time for another answer, though. I want to make sure that we get to our next presentation. So maybe you can take a look at some of those questions, Catherine, or people can reach out to her afterwards to ask a few more of those. But your presentation was really great. Thank you so much. And I think with that, we'll transition over to Jessica from Clemson, and she'll be our next presenter.
All right. So hi, everyone. I'm Jessica. I'm a PhD student in the Popet Lab at Clemson University, and I'm going to be talking to you guys about our wastewater-based epidemiology of SARS-CoV-2 in 3 of our Clemson area sewer sheds. So first of all, I'd like to start by thanking all of the people who have been contributing to this project. As all of you are very well aware, it takes a lot of people in order to make this work go. We've had a lot of people contributing not only across our own department, but across different departments at Clemson and also outside of Clemson. So we know from other studies that monitoring sewage for wastewater-based epidemiology purposes can enable us to determine if COVID-19 transmission is imminent, actively underway, or in decline. And as such, our initial goals for this project were to monitor virus levels in our campus wastewater in order to provide an early indication that active transmission was underway amongst our student body. And we also wanted to use our results to inform campus policy and also inform the surrounding community. And our overarching goal was to use our unique location to better understand how the detection of SARS-CoV-2 RNA in wastewater relates to an estimated number of community infections. So not just the number of cases that are reported, but the total number that would be present in our community. So I mentioned our unique location. A little bit about Clemson University for those who aren't as familiar with us. We're located in Clemson, South Carolina, which is in the upstate of South Carolina. We're fairly rural. The closest bigger city is Greenville, South Carolina. It's about 45 minutes away. The city of Clemson has a population of about 15,000 people. The university has a student body of about 25,000 students, and about 60% of those students live off campus. So in our general area, we have 3 sewer sheds that service the university and the area surrounding the university. The first one is our Clemson University wastewater treatment plant. This treatment plant was our initial focus because it services only or primarily the Clemson campus, as well as a smaller residential subdivision adjacent to campus. The wastewater that comes into this plant is largely kept separate from stormwater. And so we were able to minimize the impact of wet weather events on the concentrations that we were detecting. The other 2 wastewater treatment plants we started to sample were the Cochrane Road wastewater treatment plant, which services about 1/2 of the city of Clemson, as well as including in that area a very high density of off-campus student housing. And then the second off-campus wastewater treatment plant was the Pendleton Clemson wastewater treatment plant, which services the other half of the city of Clemson, as well as the town of Pendleton. This service area includes more of a mixture of residential neighborhoods and some off-campus student housing. Both of those last 2 wastewater treatment plants do have combined sewer systems too, so stormwater was an impact on those plants. None of these plants have any major industrial discharges, however, which was advantageous to us. One other component of looking at these 3 sewer sheds is that the Cochrane Road and the Pendleton Clemson service areas closely align to the 29631 zip code as shown by the outlined black dashed lines here. And that was important to us because the South Carolina DHEC reports COVID cases by zip code. And so we were able to relate the concentrations that we were seeing in these wastewater at the headworks of these sewer sheds to the number of reported cases based on our zip code. And so our overall sampling methods is that we were collecting weekly or bi-weekly samples from the end of May in the case of the university wastewater treatment plant, or mid-June from the other 2 wastewater treatment plants. We were collecting 24-hour composite samples that were about 500 milliliters each, stored at 4 degrees. We did not have the methods or the protocols or the labs in place when we wanted to start sampling. And so we ultimately decided to send our samples off for detection. So our samples went to CIREM. I know methods have been a big focus of these webinars, however, so I want to give a brief overview of what those methods were. CIREM took a portion of that sample, they pasteurized it at 60 C for 30 minutes. They performed a PEG precipitation. They extracted the RNA with triazole TM, and then they isolated the RNA for RT-qPCR. They amplified the ORF1AB, N, and S genes, but our quantification results are based on the N gene amplification. And they included several controls, including MS2 bacteriophage spikes, plasmids containing N gene fragments at different concentrations, and purified SARS-CoV-2 RNA spikes at different concentrations, as well as no template controls. And so this is kind of big picture, all of our results to date. The y-axis is the virus copies per liter of wastewater on a log scale, and the x-axis is the sampling date. One of the things I want to point out initially is that we were getting below detection limit on our first samples that we took from the university wastewater treatment plant, and so we were able to get a good baseline detection for that. Our other samples, however, when we first started collecting them at Cochrane Road and Pendleton Clemson, immediately had quite high concentration levels. And so I want to address what these concern levels are first before going back and talking about the rest of these results. So we based these values on earlier studies that were indicating values approaching and then exceeding 10 to the 5th copies per liter were indicative of an imminent rise in cases. And as such, from our concern level 3, that was that 10 to the 5th copies per liter. And above that became our major concern levels above 1 million copies per liter. And then anything below or near detection limit was our lower end. And we ultimately initially developed this as a tool to communicate these results to the public and to policymakers. We wanted to try and have some way that was easy to talk about our results with the people who were going to be making the bigger and broader policy decisions on campus and in our community. And so looking at our overall results, this was detection over the summer. And so for the campus wastewater treatment plant, those blue lines, they stayed pretty much at the detection limit or below the detection limit or very close to it. And Siren's detection limit improved over time, which is why that dotted line decreases. We were somewhat surprised that we were initially detecting a high number of, or high concentration immediately in the off-campus, because there was an assumption that most of the students had returned home. But when we dove into it a little bit further, there was a good number of undergraduates who remained in the area, and we believe that's why it was immediately a very high concentration in those two service areas servicing the Clemson community outside of campus. There was a students returned to campus on September 14th. Classes had already started online, but we're going to return to a hybrid mixture of instruction on September 21st. And so any on-campus residents were allowed to move back in on the 14th. We immediately saw a big increase from below detection limit in the campus wastewater to what we were designated as a concern level 3. Those concentrations stayed fairly high throughout the semester. Students went home for Thanksgiving and were instructed not to return. All classes moved online for the remainder of the semester, as many universities did. And we did see a decrease again in the concentrations in the university wastewater. But as students have come back, we're starting to see that increase yet again. So one of our major goals was to be able to relate this to outcomes in the community. And so from our early sampling, one of our first outcomes was the passing of a mask ordinance in the city of Clemson in the town of Central. The state of South Carolina does not have a statewide mask mandate, and it is up to different cities and towns in order to pass mask mandates. When these concentrations were returned at concerning levels almost immediately, that was one of the reasons cited by the city of Clemson when they wrote this mask ordinance, that the testing of the city's wastewater indicating elevated levels of the virus in our community was one of those reasons that pushed them to not only implement the mask ordinance at first, but to continue to extend it a few different times since then, as it was set to expire. Our second outcome was that we created a dashboard. So this is found on the same site as our reported cases dashboard. We call it our COVID-19 wastewater testing dashboard. This shows the 3 service areas that we have for the 3 different wastewater treatment plants. We use the same concern levels, but in Clemson colors, of course, with the darker, the purple, meaning there were lower detected virus in the wastewater for the week. And the darker orange it gets being higher concentrations detected. And this snapshot was taken from December at a time when the levels on campus were lower. We started this early September, so around the time when classes were getting started online. It's been updated weekly, and it's our method of communicating the results to the public and the student body at large. So moving on kind of from our community impacts, I want to talk more about what we're doing to determine a method that could be used to estimate the number of community infections, so not just reported cases, but the total number of infections in the community based on the RNA concentration in our wastewater. We have a preprint available on medRxives, and ultimately we developed a SEIR model to take into account the mass rate of RNA entering the wastewater treatment plants to estimate the number of infected individuals in the sewer shed. And I would like to specifically acknowledge Dr. McMahon here, who is a professor in the School of Mathematics and Statistical Science here at Clemson, who has led the way on developing this model. And so a little bit about what an SEIR model is. It's commonly used in epidemiological studies. It bins people into 4 different bins: susceptible, exposed, infectious, and recovered, and is used to then model the progression of a disease throughout a community. We were able to modify this to use the mass rate of RNA that was being detected in the wastewater to figure out how a disease progression would go through the community. It accounts for uncertainty in fecal production rate, in the density of SARS-CoV-2 RNA density in feces and also in the decay rates in sewage during transit. However, one of the big assumptions is that recovered individuals are no longer susceptible, but that could be modified in this model. And so looking at kind of that model results, the x-axis here is time in days, and the y-axis is the proportion in each of those bins. And so as the number of susceptible individuals decreases, you see a rise in the exposed and infectious individuals and ultimately an increase in the recovered. The model parameters included the start of the model having 99.99% of people in the susceptible bin, 0.005% started in the exposed, and the equal amount in the infectious bin. We assumed a median incubation time of 5 days and a median infectious period of 10 days. And we tried this at different numbers for the number of people who would become infectious or become exposed from each infectious person. We went from 1.5 to 2 to 2.5, and this is the scenario in which it's 2. We also wanted to look at how to use a simplified model that would be an easier way to relate a mass rate of RNA in the headworks immediately to determine an estimated number of infected individuals for a given period of time. And so this was that simplified model. It uses the average flow rate at the wastewater treatment plant and the concentration of RNA detected, and then is divided by the fecal production rate and the concentration of RNA in feces. And those A and B values we set based on literature values of 129 grams per person per day, which was a median value, and then a maximum density of copies in feces at 4.7 times 10 to the 7th. And so this is another outcome from the model. So the x-axis is the mass rate of RNA, so copies per day in the wastewater. And the y-axis is the estimated number of COVID cases. The blue line shows the median of the model. Each of those little gray points is a different simulation of the model. So that blue line is the median. The green lines are the 75% confidence intervals, and the red lines are the 95% confidence intervals. When we took mass rates along this x-axis and calculated an estimate using that simplified model, those are represented by the blue points, and those fell within the 95% confidence intervals. We also attempted another way to validate the model. There was a period of time where the faculty, staff, and graduate students on campus were being tested before they could return to campus. And the percent positivity during that time was 2%. So we made the assumption that if 2% of the population was infected, and we correlated that with the mass rates that we were detecting during that period of time. And those are the red dots. And all of those also fell within the 95% confidence intervals of our model. And finally, one of the last things I want to touch on is that we're working on figuring out a way to better kind of divide our concern levels. And so one of the ways that we've suggested to do this is to use this table, which takes the percent infected and multiplies it times that grams of feces per person per day using a median value times the copies per gram of feces and using that the maximum value, and to get these threshold levels of copies per person per day. And then we could take the mass rate of RNA entering the wastewater and then calculate the copies per person per day, and then determine from there what that concern level should be, and then use that concern level that it falls into as your way of communicating with the public at large and city administrators in your area. So overall with us, our current goals are to continue wastewater surveillance in order to provide more information about current transmission levels to the community. We want to generate a more robust data set that we can then use to further validate our SEIR model and to refine our threshold values. And ultimately, in conclusion, we know that wastewater-based epidemiology can serve as a leading indicator of COVID-19 infections. We know that it can inform public policy, as in our case, in the passing of the mask ordinances for the city of Clemson and the town of Pendleton. And we know that virus RNA levels in wastewater can be used to predict the number of infected individuals, taking uncertainty into account. We also know that the virus has persisted and continues to persist in our area. And we are hoping to be able to use this wastewater-based epidemiology tools in order to assess the effectiveness of the vaccine as it continues to roll out. So at this time, if anyone has any questions, I'd be happy to answer them.
Thanks so much, Jessica. That was great. So first of all, I'd like to congratulate you for doing this work. It's not easy. I think one of the questions already is relating to that. Maybe let's start with Colleen's question. So how did you get buy-in for doing this work and for making the data public? How did you go about this, and what were the experiences that you made along the way?
There's been, I've been less involved in the conversations with some of the university officials. That's kind of been the role of our department head. He's been the one to kind of push to be able to like make this really public. The dashboard seems to get good feedback. I know, especially the people at the wastewater treatment plants, they really like it. They like being able to show that they're contributing to this as well. I think just making the dashboard clear too, I think it was helpful that we were able to show those different service areas and try and connect it to like what is university versus the greater community, has been important for communicating those results to the public and to the stakeholders. I think it also it is in combination with the reported cases too. And so having those things be aligning also helps, and just like provides that extra depth that, the cases aren't necessarily wrong because the wastewater is also showing similar trends.
Yeah, well, I think for it's an unusual location, right? Because you have such a huge student population. If you think economically, the impact on that area, the campus really drives whether this city is alive or dead. And so the burden, the political weight on that, on the data is huge. So it is amazing that it was pulled off in this environment. If you can think of a city that's more robust, more diverse, a campus doesn't matter all that much. But here the campus is driving the entire economic activity. So that's interesting. Do you think that's just a mindset, or is there something special about Clemson, city of Clemson and Clemson University that made this possible?
In what way? I think
I don't know, because we are just curious, because some of us try to do monitoring or get data out, and they're struggling to convince decision makers that the data should be public and that people should look at it. So, but you didn't encounter any of that, so it was just.
I think we have a lot of people pushing to make it public, and a lot of people, especially like within our department. Dr. Friedman in particular, our department chair, has been very forthcoming in wanting to make sure that this is public. And I think that helps to have that support and that leverage when talking to our university administrators.
Yeah. Another question for a small campus. So what we have observed internationally too is that the wastewater flow on a campus is fairly stagnant, or at one level, and the population really varies quite a bit, but it doesn't register as much. So it's more difficult to normalize for a population. Can you relate to that, or do you feel that sewage flow is a good indicator of population count for your particular location?
I think one of the things that we want to look on in the future is having a better idea of exactly how many people are being counted, especially when we can look at the university campus itself, because you kind of have an idea of how many people are on campus at a given time. So I think being able to have that small plant that we know exactly who's on campus, how many people are using it, and we're hoping to be able to relate that better to the trends that we're seeing.
Yeah. Okay, we have a question here from Tracy Fielder. I'm not sure you can answer this, but I will read it to you. In the UK, an unofficial method of tracking the B117 variant is by looking for a dropout in the S gene. Do you know if you use the same primers?
I'm not sure. I'm not familiar with that study yet, so I would have to check.
Okay, and maybe another question, the cutoff levels. I think conceptually it makes a lot of sense to bring some structure into this, right? Because there's a continuity, and we're wondering at what point, do we have to do something extra, right? Or are we just sitting there and watching the data roll in? They have to be actionable. So I think a lot of us like the idea of having different levels, but of course then you have to set this arbitrary level, and then set another one. Can you walk us through the thought process of, or how it came about that you decided on so many levels and where to draw them? And do you feel that it's robust, given that if the population count, might be off, and then obviously that changes the level of concern too? Do you want to comment on that?
Yeah. So one of the things one of the things I didn't mention is like the big caveat is that because that initial leveling that I showed was based on copies per liter, you will have to take into account the various sewer sheds. If there is more stormwater coming in, if there is more industrial discharge, then those flow rates are going to be a lot higher. There's going to be a lot more dilution effect. And so that's why we were trying to create a table that would be basing those levels more on a mass rate rather than on a copies per liter, because that mass rate will then take into account flow rates too. That initial one that we used kind of in the beginning, it was a work in progress. It's still a work in progress. I think we can still do better at refining those levels. But that was mostly based at looking at a couple of different studies. One was in Valencia, Spain in particular, that we've looked at a lot, that it was really showing once that threshold reached over 10 to the 5th, cases soon rose alongside of that. And so from there, we decided to do the, a log threshold. And with that 10 to the 5th being the intimate transmission occurring.
Yeah. Great, thank you. There's another question coming from Ted Smith here relating to temperature. He asked, one of the challenges in the change in temperature during this period is degradation of the samples due to temperature gradients, possibly influencing the estimation.
We don't think so. Or one of the benefits to us being a smaller community too is that our transmission times from toilet flush to reaching the headworks, like the furthest is about an hour. And so the times are really low. I don't think it would be sitting in there long enough to really like heat up in transit before we collected those samples. We haven't seen, it's not like we saw a lot lower concentrations over the summer and then they increased as it got cooler. It's kind of stayed about the same. So I don't think that is really having too much of an influence.
Yeah. And
in that decay model too, the temperature could be added into that.
Yeah. Okay. So I completely agree also with if you have a very short residence time, then there isn't that much opportunity for degradation in the first place, and then obviously for temperature to modulate that degradation. So campus studies, small communities are a better target and more robust in that respect. I think we can agree on that. Maybe one more question, maybe regarding your model. Models are great, right? Models can be useful. Models are also vulnerable. And I think the first question a lot of us ask when we look at modeling data, so where is the big uncertainty? What parameter drives the uncertainty in your model? Can you give us a sense of, and that relates to everything, not just the parameters you show, but sometimes also the values you have to plug in, right? Whether it's the amount of feces produced per day, or the copy number, or the duration of people excreting the virus. What is your sense of what drives the uncertainty of the model result overall?
I think I would probably have to refer to Chris on that one. I'm not sure exactly which one would be the most driving it. I think all of those we determined had some influence. And so we wanted to account for all of those uncertainties. I can show you, this is another figure that we had. And so this was kind of our part of that model where we were showing the predictions for the mass rate over time. And so this would have helped takes into account all of those uncertainties. And so it shows you how different that mass rate could be with all of those uncertainties included.
Yeah. And it's a remarkable spread, right? So there's, it is quite broad. Yeah. But this is great. And so I can, looking at this type of information really helps to understand the possibilities, also the limitations of modeling. All right, I think we have exhausted all the questions, Jessica. Thanks for a very intellectually stimulating talk. And yeah, we're happy to see that you are able to carry out this work. If you have any recommendations for others, please continue to share them. And back to Ali.
Thank you so much for letting me.
Yeah, special thanks to Jessica and Catherine for sharing their work. It was great to hear about it. Nice work, everyone. And we have another webinar coming up in a couple weeks, which Jill will email you about. So thank you everyone for participating, and we'll see you later. Bye-bye.